difference method, we discussed about its derivation, and we also discussed that log mean temperature difference is employed where the inlet and outlet temperatures are known to us, and we need to know the size of the heat exchanger which is required to have that particular change in temperature. So, if we can revise what we discussed yesterday on the whiteboard, so the rate of heat transfer in heat exchanger, that is equal to Q dot is equal to U into surface area into delta T mean. Now delta T mean, it can be logarithmic, it can be any temperature difference. So for the log mean temperature difference, we know that this delta T m is equal to delta T logarithmic. So in this, we considered parallel flow double pipe heat exchanger, and then we took a differential area here, which is of surface area dAs, and then in that differential area, uh, the heat is being transferred from the hot fluid to the cold fluid, that is shown by this three red arrows, and that would be equal to delta Q is equal to U into TH minus TC into DS. Here TH is the temperature of the hot fluid and TC is the temperature of the cold fluid. So then we discussed that delta T1 is the temperature difference at the inlet, which is the TH in minus T cold air, and then similarly delta T2 is TH out minus T cold out, and DTH here you can see that is the temperature decrease in the hot fluid in that differential surface area, and then DTC is the temperature gained by the cold fluid in that differential area. And so if we first of all, if we write the heat which is being lost by the hot fluid, that would be equal to minus m dot h cph into dth. The minus sign is here because dth, if you see here, that is being decreased, so it means that it would be negative, and so it means delta q which is being taken away from that from the hot fluid, that would be equal to the same heat transfer which is gained by the cold fluid, which is m dot c into a specific heat at constant pressure for the cold fluid into DTC. DTC is the temperature change happening when the fluid travels from in this differential area. So it is also shown in this figure. And now if we want to write DTH, we can say that DTH is equal to minus delta Q upon m dot H CPH from this first relation, and similarly DTC is equal to this. And if we do the mathematical manipulation, which is if we take the difference of the temperature change between the cold and hot fluid when they pass it through that differential area, that can be written in terms of delta Q by this relation. And we did all this on the whiteboard in yesterday's class. And then if we put the value of delta Q is equal to U into TH minus temperature of cold fluid into DAS. So, and then if we do the separation of variables and do the integration, we come up with a logarithmic function here, because we know that if there is a dx upon x would be equal to natural log of x. So here x is th minus tc. So in this case, if we do the substitution which we did in the last class for the m dot h cph we can write Q dot into TH in minus TH out, and similarly for M dot C CPC we can write Q dot upon TC out minus TC in. From where this came, if we remember that these relation we write here, okay, TC out minus TC in, and similarly TH in minus TH out would be from here we can see M dot C into CPC value and M dot H CPH value can be equal to Q dot upon TC out minus TC in, and similarly for the hot fluid. So if we replace that values here, then we can write it in terms of Q is equal to UAS into delta T logarithmic, and here delta T logarithmic is delta T1 and delta T2. So these delta T1 is the temperature difference at the inlet, delta T1 between the hot and cold fluid, and delta T2 is the temperature difference at outlet for the hot and cold fluid, right? Uh, and this derivation was done for the parallel flow arrangement. If you can see here, this is the temperature variation for parallel flow double pipe heat exchanger. The same thing can be done for the counterflow, and we would come up with the same relation even for counterflow uh, heat exchanger flow arrangement. And then the only difference here is the definition of delta T1 would be different. For the case of counterflow, here delta T1 would be equal to TH in minus TC out, and then delta T2 would be equal to TH out minus TC in. So that definition is a little bit different for the counterflow, otherwise all other things are same. And now we are going to do a couple of numerical problems for log mean temperature difference method. So if there is any query, anything you couldn't understand from the yesterday's class, you can let me know. Otherwise, we can continue with the numerical problems. Okay, so this is the first example problem, that a counterflow double pipe heat exchanger is exchanger is to heat water. Uh, CP value is given from 20 to 80 degree and water is coming in that pipe at 1.2 kg per second. The heating is to be accomplished by geothermal water, whose CP value is also given, available at 160 degrees centigrade at a mass flow rate of 2 kg per second. The inner tube is thin walled and has a diameter of 1.5 centimeter. Now, when we say that the inner tube is thin walled, it means that we are going to ignore the conduction resistance of the pipe, because secondly, because the for that pipe there is no K value given, so it means that we can ignore the thermal conduction resistance, because thermal conduction resistance for the pipe is natural log of d outer upon d inner divided by 2 pi KL. So you can say that here when we say that inner tube is thin walled, so we are going to ignore that the thermal conduction resistance. If the overall heat transfer coefficient of the heat exchanger is 640 watt per meter square centigrade, so they have already given U value. Determine the length of the pipe, length of the heat exchanger required to achieve the desired heating. So here we need to determine the size of the heat exchanger, and we are given the temperatures for the hot fluid and cold fluid at inlet and outlet low. So let's see that if we can here we can kind of draw the schematic. So bear in mind that this is a parallel flow heat, counter flow heat exchanger. So so here I would say that TH in is entering, and here TH out is going out. And because this is a counter flow heat exchanger, so it means that cold fluid would come from the opposite direction. So it would come from here, and it would go out from here, TC out. So if we can write the values for that, so here if you see that the water is to be heated, so it means that this is water is a cold fluid here, so 20 to 80 degrees. So if we say that at cold water in is 20 degree and uh, cold water out is 80 degree, and then geothermal water is to be used for that heating. So it means that geothermal water is a hot fluid. So in this case, it is inlet temperature is 160 degrees centigrade. So THN is equal to 160 degrees centigrade, and the mass flow rate for the uh, m dot c is for the water, that is 1.2 kg, and for the hard fluid it is so m dot c is 1.2 kg per second, and m dot h, which is geothermal water, that is 2 kg per second. Now, first of all, we don't know th out because that is not given in the data. And what else have been given here? That we have been given the diameter of the pipe. Yes, that is 1.5 centimeter diameter is given. So this diameter is 1.5 centimeter. So now, first of all, if we remember that for the logarithmic temperature difference, the formula is Q into UAS into delta T logarithmic. So delta T logarithmic here is equal to uh, delta T1 minus delta T2 upon natural log of delta T1 on delta T2. Now delta T1 here would be equal to TH in minus TC out, and delta T2 would be equal to, if I write delta T2 somewhere here, delta T2 would be equal to T, it would be equal to TH out minus TC in, right? So these are the two temperature difference, but here TH out is not known. So once we get TH out, if we can find th out, then it means that we would be able to find delta t logarithmic. So it would be known. U is given in the data, so that would be known. If we can find q dot somehow, that would be, then we can find surface area. And when we find the surface area, then surface area is AS is equal to pi di, pi dl. So from here, length can be determined, which is required for this problem. That the length of the that pipe for the heat exchanger we need to determine, that would produce the required heating. So we first of all we determine q dot. So q dot for the cold water which it would gain, so that would be we can say that Q dot for the cold water would be equal to m dot C into CPC into TC out minus uh, cold fluid inlet temperature, which is TC in here. So m dot C is, if we remember, m dot C is 1.2 kg per second. 1.2 into CPC is given, that is 4.18 kg. So we can either write it as 4.18 kg. We keep it like this, and then the uh, we would have the value in kilowatts. So TC out is 80 minus 20. We would get one value here, some value, and from there we can, because this is the heat which is gained by the cold fluid, so that would be the same heat which is being given by the release by the hot fluid. So now we can also write that Q dot is equal to m dot H into Cp H into Th in minus Th out. So from here we know Th in, that value is 160. Cph is given in the data, and then m dot h is also given in the problem statement. Then Q dot we have calculated from here. We can put it here, so we can find Th out, and once we get Th out, then we can find delta T1, delta T2, delta T logarithmic, and then we can find the AS value. And AS would be equal to pi dl. So diameter is given 1.5 centimeters. So we would be able to find the length which is required to achieve the desired heating. So if we see the numerical values here, now I have explained regarding the calculation procedure. So now we can see the exact derivation here. So numerical calculation here. So first of all, we need to find Q dot for the cold fluid, that would be equal to m dot Cp into T out minus T in. So 1.2 into 4.18 into 80 minus 20. So it would be equal to 301 kilowatt, and then this is the same heat which is released by the hot fluid. So here we can see that we can find Th out, which is not given to us, so that would be equal to Th in minus Q dot upon m dot Cp. So it means that the geothermal water would be cooled to 125 degrees centigrade in this process from 160 degree, which was inlet temperature. So now we know this, and once we get this, we can find delta T1, which is Th in minus Tc out. So Th in is 160 minus Th out. Tc out is 80 degree. So delta T1 comes out to be 80 degree, and delta T2 is equal to Th out minus Tc in. So that would come out to be 105. So here, if we find that delta T logarithmic, so that would be equal to log mean or logarithmic, we can call it. Uh, Here it is written delta T LM, so it means that we are talking about log mean. So if we do that, delta T log mean comes out to be 92.0, and now we can calculate Q dot is equal to UAS delta T logarithmic, and here because we know all other quantities, so we can find the value of AS, which would be Q dot upon U into delta T log mean. So that value come out to be 5.1, and surface area comes out to be 5.11 meter square, and from here we can find the value of length. So length can be find out, and you can see that the value is 108 meter. So we can readily see that, or we can easily conclude that this length cannot be like one straight pipe, because 108 meter that pipe usually requires some kinds of bends or networks of bends by having some network of tubes. So to accommodate that heat exchanger process in a limited volume, so that's why in practical applications we usually have shell and tube heat exchanger, because they contain a network of pipes or many passes of pipes within a limited volume. Okay, ji. Anything which is not clear here? If you have got any query, you can ask me now. And similarly, we can have the another numerical problem related with this. So it is almost the same. If you can read the statement, a thin walled double pipe counterflow. Now again, counterflow heat exchanger is to use to cool oil. So now we are trying to cool oil from 150 to 40 degree and oil mass flow rate is 2 kg per second, and we are using water to cool it. So it means that here this oil is the hot fluid, and the water is the cold fluid that enters at 22 degrees centigrade. Now for the cold fluid the inlet temperature is known, but the outlet temperature is not given. Right, so the diameter of the tube is 2.5 centimeter and its length is 6 meters. Determine the overall heat transfer coefficient. So now first of all we need to determine the outlet temperature of the cold fluid. So by using the same methodology as we did here, that first of all we determined here, we are going to determine q dot is equal to m dot h cph th in minus th out, because here oil is the hot fluid, and so we would get q dot, and from the calculation of q dot we would be able to get the outlet temperature of cold fluid, which would be water here. So once we get that, then in this numerical we would be able to find the value of delta T logarithmic, and AS can also be calculated, because now the length is given in this numerical. So the only unknown that would be U. So that is kind of the similar identical problem which we did. So we just quickly go through this. So q dot would be equal to m dot cp t in minus t out. It is for the oil at the it is for the hot water, which is oil here. So hot is hot water, that is oil, or not hot fluid, that is oil, 150 to 40 degree. So you can see that th in is 150, th out is 40 degrees. So it would comes out to be 484 kilowatt. Now we can find the value of cold water outlet temperature, which is TC out. So that comes out to be 99.2. So it means that the cold fluid is heated from 22 to 99, right? While the hot fluid is being cooled from 150 to 40 degree. So once again we can find delta T1, delta T2 and delta T log mean by the relation, and then by using the Newton law of cooling, q dot is equal to UAS delta T logarithmic U can be calculated, which is the overall heat transfer coefficient. So which means 32.5 kilowatt per meter square into centigrade. Now we have found out U. So now it means that we need to have the material of the heat exchanger in such a way that this U value should remain in this range because we need to have that heat transfer. So just a physical aspect of design that, sorry, because we know that U is equal to, if I ignore the area, then that would be equal to 1 upon HI plus 1 upon H outer uh, plus that conduction resistance for the R conduction. So in which we have got log of that. So this is natural log of d outer upon d inner divided by 2 pi k n. So and if we do that, now it means that this HI and HO would be calculated by the knowledge of, this would be calculated by knowledge of chapter number 8 and chapter number 7, which we have discussed up till now. And this, in this, the material of the pipe should be selected like that U value comes out to be equal to 32.5 or more than that, to be on the safe side. And the thickness of the pipe also comes into play here. That thickness of the pipe should be such that it can have U value equal to that the numerical value which has been calculated here. So calculation, just for the sake of these calculation for the overall heat transfer coefficient, that is quite straightforward. We can do it very easily, like in 10 minutes time. But when we design it for actual heat transfer, actual heat exchanger, now we need to look at the thickness of the pipe, and then secondly the material of the pipe. And then one thing we also need to cater for, that is the fouling factor, right? Because when once it is new, for the new heat exchanger, there wouldn't be any fouling factor there, any accumulation of deposits. But once in operation, maybe in couple of years, there would be some fouling. So we have to cater for all these factors. So once we get the thickness, then we need to do stress analysis as well on that pipe to see that whether it wouldn't cause any rupture in that pipe. Because if it is too thin pipe, there would be some problem of leakage of that fluid which is passing through it. So all these considerations are taken to be into account when we do this thermal analysis. So doing the crux of discussing this thing is that calculating these values are quite straightforward, but then implementing it into a practical actual design requires quite thorough thinking about different parameters which are used in uh, for these parameters like U and like overall heat transfer coefficient. So I hope that you get a crux of what I am trying to say. So these were two numerical. Now all these derivations which we have done here, that is only for double pipe heat exchanger, either for the parallel flow heat exchanger or counter flow heat exchanger. So, but in the practical problems, we usually have either compact heat exchanger in which there are fins, and then there are other problems where we have got cross flow over tubes or shell and tube heat exchangers. So, in order to apply this analysis on those types of heat exchanger which are generally used in industry, we need to have some complex analysis. But because that is not required, because complex analysis can be done by using software, but for the for the sake of rough estimates, people have come up with some correction factors which needs to be applied on this analysis, so that we can get the values for for those practical cases, like shell and tube heat exchangers and multi-pass heat exchangers, and then cross flow over tubes. So what is that correction here? The LMTD method explained earlier is for the double pipe heat exchanger only. For multi-pass shell and tube or cross flow heat exchangers, the log mean temperature difference is multiplied by a correction factor. So people have found out that if we multiply it with that correction factor, then we would be able to roughly predict the value of heat transfer, right? So their correction factor is represented by F. So it means that in the original formula, we introduce a correction factor for Q dot, that is Q dot is equal to UAS into this capital F, which is correction factor, and into delta T log mean count for the counter flow. Here CF is the counter flow flow arrangement, right? So now how to calculate F? This F is the correction factor. So for that we use that inlet and outlet temperatures of the hot and cold fluid. So we use two parameters for the calculation of this correction factor. One is we call it R parameter, and then the other parameter is P parameter. They are the ratios of temperature differences. So we would see to that. First of all, now you can see there are two terminologies here. One is uh, one and two. So one mean inlet, two mean outlet in these formula for the P parameter and R parameters. And then there is capital T and small t. So capital T is the fluid which is passing through shell site, and small t represents the fluid which is passing through tube side, right? So shell side is the outer bigger pipe, and tube side is the inner tube which is of small diameter. So now you can see that if we want to calculate P, that would be equal to the difference of temperature, outlet temperature of the fluid at the tube side, minus inlet temperature of the fluid at tube side, divided by inlet temperature of the fluid at shell side, minus inlet temperature of the fluid at the tube side. So here, if you see in this notation, here the graphs are given. Now we can see that now for one shell pass and multiple tube passes, these are the graphs. And R is similarly capital T1 minus capital T2 divided by small t2 minus t1. Now, for the convenience of the understanding, they have also shown this capital T1, capital T2 on the schematic as well, and small t1 and small t2 here. Now, if we talk about that, how to read this graph, let me. I hope that you can see this. Maybe we make it to see. Okay. Now maybe it is a little bit better. So now on the x-axis we have got P parameter. Here P is written. The formula is also written and schematic is also shown here. And then on the y-axis we have got correction factor. So we have got on x-axis p parameter. If we know the p parameter, let's suppose we have got, and different curves of r are given on this graph. So let's suppose we have got the value of p, that is zero point 0.5, and r value is equal to 1. So what we will do, that we draw a vertical line on this graph, and we extend that line to the curve where r is equal to 1, and then where it intersects we just uh, draw a horizontal line to read the value of correction factor. So if it is zero point 0.5 in this case, p is zero point 0.5 and r is 1, so you can readily see that correction factor would be equal to, from here it would be equal to zero point 0.8. Now the question is, what if the value of r is something which is not between zero point 0.2 and 4? Then if r value is zero point 0.1, then correction factor would be equal to 1, and if r value is more than 4, then even in that case the correction factor would be equal to 1. So we can only read the values when we have got the value of r and p, they are going to intersect each other. If there is no intersection for the values of p and r, like I said, that if we have got the value of p equal to 0.95, so no matter whatever value, if p is 0.95, no matter what is the value of r, there is not going to be any intersecting line which can have the intersection of r with p. So it means that in that case, the value of correction factor would always be equal to 1. So I hope that this point is clear to you all. We would do one numerical now. So this graph is for one shell pass and multiple tube passes. Similarly, for the two shell pass and multiple tube passes, we have got a different graph in which we have got R and P curves, R curves on this, and then similarly for the single pass cross flow with both fluids unmixed, we have got another graph from which we can calculate friction factor, and similarly for the single pass cross flow with one fluid mixed and the other unmixed. So that is the case of the radiator flow over a radiator. So in this case, if we want to know about the friction, that correction factor F, that can be calculated from this graph. Now we quickly see that how to read the value of F for a given problem, or how to calculate R and P parameters. So now we have got two shell passes and four tube passes. Heat exchanger is used to heat glycerine from 20 degree to 50 degree centigrade by hot water. So here the cold water is glycerine and hot water is hot fluid here, which enters the thin wall tube, uh, 2 centimeter diameter tubes at 80 degree and leaves at 40 degree. So now we have been given inlet and outlet temperature for both the fluids. The total length of the tube in the heat exchanger is 60 meter. The convection heat transfer coefficient is 25 watt on the glycerine side, which is shell side. So it means glycerine is the on the shell side, and the water is on the tube side. So that H value, it would be H outer 25 and H inner would be 160 watt per meter square. So now we need to calculate the rate of heat transfer before any fouling occurs. So it means that we don't need to consider the fouling factor here, but the, then for the second case, when there is some accumulation of solids on the outer surface of the tube. So we are talking about here somewhere on the outer surface of the tube. So we need to do that. So first of all, here delta T logarithmic calculation is quite easy. AS can be calculated pi dl. We know diameter and we know the length of the tubes. And then here if we see that AS is known, delta D log mean for the counter flow, that can be determined very easily, because we know that it is entering at 20 glycerin and it is heating up to 50, and then delta T1 would be equal to TH in minus TC out, which would be 80 minus 50 here. So you can either take delta T1 this point or this point, it doesn't matter. The both results would give us the same thing. I mean to say that it can also be taken delta T1 and this would be delta T2, or we can take this as delta T1 and delta T2. So if we do that, so delta T log mean can be calculated. So the only thing which is here, the two things, one is U, that is not known to us, and then this correction factor. So for the calculation of correction factor, we need to have the value of P parameters. Now on the tube side, we have got water, which is used to heat the glycerine. So water outlet temperature is 40, water inlet is at 80. So T2 minus T1, small, I am talking about numerator, and then on the denominator side, capital T1 is the inlet fluid temperature at the shell side, which is glycerine. So that was 20, 20 minus 80. So if we do that, P value come out to be equal to 0.67. Similarly, R value comes out to be 0.75. So now R value is 0.75 and it is 0.67. So if you see here that I have drawn a vertical line here, which is at 0.67, and then I would go, because here we don't have any curve for 0.75. Either we have got a curve at 1.8 and 0.67. So what I would do that I would kind of consider a imaginary curve at 0.75, which would lie near this 0.8 curve, and then I would take 1 point here, and if I see that value, that would be almost equal to 0.91. So if you take it as 0.90, 0.92, 0.93, 0.94, that would be equally correct. But you cannot say that this value is like 0.97, because uh, the data should lie between the two limits, the two curves of zero point 0.8 and zero point 0.6. So that is around in the range of 0.91 to 0.94. It cannot go beyond that. Okay? So please bear that thing in mind. Friction factor is calculated, and then U calculation. First of all, there is thin wall tube, so we haven't considered the conduction resistance. U would be equal to 1 upon Hi plus 1 upon Ho. That value is given. We can calculate Q dot, which comes out to be 1.83 kilowatt. Now, the second case is that we need to consider fouling as well. So that fouling factor is given 0.006. So if we do that, U value is now a little bit less. So U value comes out to be 21.3 and Q dot comes out to be 1.8, 1805. It was 1830. So like 25 watt of heat is being lost due to that fouling of those tubes. So it is not much when we consider the original value. It was 1830, so 25 is very less value as compared to maybe uh, it would be less than maybe 5%. So but still it is some loss, so we don't need to bear that. So that's why we usually do periodic maintenance of those pipes to remove those fouling on the pipe surface, so that there is no loss of heat transfer due to fouling. So this was it. So we discussed about the log mean temperature difference and its practical application for shell and tube heat exchanger and cross flow tube cross flow heat exchanger. So if there is any query, you can ask me now. Uh, so otherwise, let me download the attendance and then. Okay, one announcement. We would have a quiz in next Friday's class. Okay, no, not next Friday, but next Wednesday class, which is like 1 week from today. From this heat exchangers chapter, which is chapter number 13 of this book. So, is there any query from today's lecture?
सर ये कौन सी बुक से पढ़ा रहे हैं आप ये चैप्टर 13?
Who is it? Bilal Maqbool?
हैदर सर।
हैदर। ये जो सेंजल की बुक है ना, जैसे चैप्टर 7, चैप्टर 6, चैप्टर 6, 7, 8 हमने पढ़े हैं, उसी बुक का अगर आप देखें चैप्टर नंबर 13 है सेंजल की बुक का ना, वो है हीट एक्सचेंजर के बारे में। तो ये वाला चैप्टर हम सेंजल की बुक से ही पढ़ रहे हैं। ठीक है,
ठीक है जी सर। जी सर, थैंक यू।
ओके, थैंक यू। So if there is no further query, we can just call it a day at this time. So